And in this particular part of the lecture, part 3, we're going to be looking at spent fuel treatment. We're going to show you what spent fuel is, what options do we have, and the difference between an open and a closed fuel cycle. Okay, so the first thing is, what is spent fuel? Now, if you think about the fuel that we manufactured originally when I showed you in that first part of the lecture on reactors and on the nuclear fuel cycle, we said that fuel is made from uranium. So chemically it's 100% uranium, but once it's been in the reactor and it's undergone fission, then the fuel is going to change chemically, and it's going to be a very different type of radioactive substance as well, because we get lots of fission products. We get those minor actinides and transuranics, the americium, the curium, and the neptunium and the plutonium. Chemically, though, the majority of the uranium remains. Essentially, what we do is convert the uranium-235 into other things. Now, the concentration of these other things, like the fission products and the actinides, does depend on quite a number of factors. So, for one thing, the actual fuel itself. It could be naturally uranium metal, as in the case of the Magnox reactors in the UK. It could be enriched in uranium-235 as an oxide, which most reactors today use. We could even have fuels that have an element of, or a certain amount of plutonium in there. They're called mixed oxide fuels. The reactor type makes a big difference as well, because the neutron spectrum in each reactor is different. What we call the fuel burn up, and this is nothing to do with chemical oxidation, it's nothing to do with burning per se. What we refer to when we refer to burning in a reactor is the amount of the fissile material, the U-235, that's being used. And also, how long has that fuel been aged for? For example, when the fuel comes out of the reactor and is stored, some of those short-lived fission products decay away, and therefore the radioactivity changes, and literally the fuel composition changes as well. But there is one thing that's undoubtedly common about any type of spent fuel, and that is it's hot, quite literally, because it's come out of a hot reactor, several hundred degrees C for a light water reactor, and upwards to 600-700 degrees C for an advanced gas-cooled reactor, and it's intensively radioactive. Now, when you make the fuel, the uranium, you can handle it manually, but once it's been in the reactor, once it's got those fission products and those actinides in there, the radioactivity is such that you cannot go anywhere near it. It's quite literally a lethal dose of radiation. So let's have a look at the composition of spent fuel, and this is, like I said, it does vary on quite a number of things, but typically we can expect the actual chemical composition to be around about still 95-96% uranium. So in fact, we've only converted about 4 or 5% of the uranium into other species, the majority of which are fission products, which are stable, so they're actually not very radioactive. We get some minor actinides, so that's the americium and curium, a small percentage of that. Depending on what the length of time the fuel is in the reactor and the neutron spectrum and the level of U-235 to begin with, depends on the amount of plutonium we get, but typically we expect somewhere in the region of about 0.91% of the fuel to be plutonium when it comes out. We get some very long-lived isotopes, some long-lived fission products like some of the iodine species, and also technetium-99, and we get those two fission products I mentioned about when we were talking about fission, cesium and strontium. So they're one of the major components of the fission products, and then you get other fission products as well. In fact, if we look across the whole of the periodic table, we can map out and look at the types of fission products we get in spent fuel. So if we have a look, we get these species at the bottom, so the transuranics and the actinides, heavy nuclei. Now, they're not fission products as such. If you remember, they result from neutron absorption in U-238 that then transmutes. All the smaller elements, these purple ones, these are fission products. So these are a result of the fragments that have resulted from a fission event. You do get some what are referred to as activation products, Remember, a fuel assembly is not just the nuclear fuel. There were the fuel cladding, which is the material that makes up the fuel rods. There was the grids that held all the rods together. There was things like the control rod cluster. Now they're usually made of zircaloy, which is a zirconium alloy, and also stainless steel. So some of the components within those stainless steels and those alloys become activated because neutrons affect their structure. So you can get cobalt 60, for example, that results from the nickel in the steel. Some of these circles here, you can see I've just circled in this particular diagram. Some of them are long-lived. So if we were wondering about storage of the fuel, or even wondering about what we do in terms of waste treatment, we know that some of these particular fission products will be around for a very long time, and therefore we have to deal with the waste in a particular way. So if you think about spent fuel overall, like I said earlier, we're not just dealing with the fuel itself, we've got all the actual hardware and the fuel cladding, which is the metal that surrounds the fuel rods, that we've got to deal with as well. So we've got stainless steel in the end appendages, the nozzles that go with this particular fuel assembly. We've got the grids that hold all the rods together, and we've actually got the cladding material itself, which is usually this zirconium alloy called zircaloy. And if we're dealing with that as a single waste form, then we need to really think about how we put that away in terms of spent fuel management and also waste disposal, because like I said, a lot of the fission products in there and the actinides themselves are very long lived, and therefore it's dangerous for a very long time. Now we can recover it because about 95-96% of the metals within that spent fuel can be recovered and used as new fuel, primarily the uranium but also the plutonium itself. So we could recover that material, and the benefits of that from reprocessing of the material compared to just direct disposal mean that in some cases it's a lot easier to deal with. So here we have a plot of the relative radiotoxicity over time, and you can see that's a logarithmic time there, so stretching out to millions of years. And what we've got is this essentially this reference here, relative toxicity equal to 1. So what we're doing is we're plotting how long does it take to get back to the material that we originally dug out the ground. So if we take our first line on the right here, this is a plot of the radiotoxicity of spent fuel. So that's all of the components. That's all of the assembly components, it's all of the plutonium, the minor actinides, and all of the fission products, because we haven't actually done any work on that. We've not separated it, or we've not chemically treated it. And you can see typically we would be talking about a couple of 100,000 years for all of those radioisotopes to decay away down to equivalent to background levels. Now, if we were to do some recycling or reprocessing work on that, and we were to recover the plutonium, we would just have minor actinides and fission products to deal with. That's a different waste form. I'll explain what that would be in the next lecture in terms of just introducing that. But there's a big difference there, because actually what we're doing is we're removing some of the long-lived isotopes, specifically one of the isotopes called neptunium-237. And then in that case, we could reduce the toxicity levels down to tens of thousands of years. Of course, that's still a very, very long time. It still means that you can't store it in a building, because we could never design or build a building for that long. But obviously it does make a big difference in terms of the way you might design your repository. Now, if we went all the way and we actually recovered all of our minor actinides and removed some of the long-lived isotopes as well, and perhaps dealt with them in a different way, we'd be left with all the short-lived fission products, things like cesium and strontium, and in fact we're down to hundreds of years then. Now the thing is, as we move from there to there, it becomes technically more demanding and more complex. So we know we can do this because countries have done that already, and we know we can do this because countries have done that already. but we don't know we can do this yet. We don't have a process that's been developed to do that. So what options do we have available to us, or what options are being developed that may be available in the near future? Well, we have what's called the open fuel cycle. Essentially, that's direct disposal of spent nuclear fuel. You package the waste up, or you package the fuel up as waste, and you dispose of it in a deep depository. We can look at closing the fuel cycle. By closing the fuel cycle, what we mean is we're going to start recycling some of the material. And at the moment, we partially close that fuel cycle because our recycle plants that are operating have operated in the UK and operate in France are able to recover the uranium and plutonium and use it as a mixed oxide fuel in current reactor technology. What we would like to do is fully close the fuel cycle. In other words, we'd be able to effectively recycle all the material that we need to and can use, and therefore save a lot of the material that we would need to dig up out of the ground. That does require minor actinide recycling, and it does require fast reactors that are able to burn these materials. And again, when I say burn, I mean use up in a nuclear sense as opposed to a chemical sense. So let's just have a look at that open fuel cycle. It's the simplest one. It's not really a cycle, obviously, because we're not actually coming back to the beginning. It's actually a linear progression. And if you think all the way back to the nuclear fuel cycle, what we need to do is obviously dig out the material to begin with. I showed enrichment on that original nuclear fuel cycle diagram. There is a step in between extraction and mining before enrichment, and that's because we need to convert it to this compound called uranium hexafluoride. So these are all common steps of any cycle, because to begin with we need to start off with material that we can use in a reactor. We make our nuclear fuel out of the uranium, we put it in a reactor, and then we effectively store indefinitely. So that's either storage in a facility above ground, and then it's packaged up and moved below ground. And what we're doing is we're using time there to get rid of the waste. We're storing in a waste repository to allow all that radioactivity to decay away. And about 85% of the reactor fleet around the world uses this particular strategy to deal with its spent fuel, although there is actually only one country that has a repository that's working. Of course, an open fuel cycle has its limitations. Ultimately, it's not sustainable, and at some point we would run out of material. So here we have a couple of plots here, one of which is showing the usable or the economic usable supplies of uranium around the world. So there's a lot of good mines, and we can see that's running up to 2017. And then once the price goes up, then we would start opening up different mines. Essentially what we're doing is we're using the high grade ores first, and this is reflected in the spot price. So I've just looked up as part of this lecture series what the spot price of uranium is from mining companies, and it's $31 per pound. So that's what you buy it on the open market, so that's actually quite low. And that's because these big mines around the world that are still operating that have rich resources that you can tap into. And in fact, there's some figures there that say that in 2019, over 60,000 tons of uranium was mined and sold to fuel manufacturers for use in nuclear reactors. Now, of course, as long as we've got access to very high-grade ores that are easy to get to, then we can carry on doing this. But at some point those would run out, and therefore the price of uranium would go up, and it would be more economic to recycle or perhaps look at different reactor designs. And people have tried to estimate this, and it does depend on the number of reactors. So here's an estimate of demand versus production, and you can see forecasting into the future. Then at some point demand will outstrip supply, and we'll have to dip into these secondary supplies here, these more expensive ones. Now, of course, also, if we're mining 63,000 tons of uranium a year, then it's not without its environmental impact. Most uranium is mined through strip mining. Essentially, the deposits are quite near to the surface, and therefore, in terms of environment, is potentially quite damaging. It's no different than any other ore. In fact, they're one of the biggest uranium mines in the world. Olympic Dam in Australia, there's a picture of it here, is kilometres square. So that pit there may be a couple of 100 meters deep. And essentially what they've done is they stripped the surface away so they can get at the very rich ore that's there. But primarily, actually, this is a copper mine, and it's been they're after some very rich copper ores there, but they just happen to be co-located some rich uranium ores there as well. So you can see the amount of open pit or in situ leaching, which is a similar process in terms of mineralogy. Most of the uranium is done by that, as opposed to very deep satellite mines you would expect from a coal mine or something like that. So potentially it's environmentally damaging. So if you could reduce that, and you could reduce the amount of uranium you needed from a fresh source by recycling, obviously you would gain environmentally as well. So an alternative is to look at recycling. And the first step is to try and recover the elements that are relatively easy to recover chemically, and that's the uranium and the plutonium. And when we do that, we refer to that as a partially closed fuel cycle. Now, the first steps are the same. We've got the uranium being mined, conversion, enrichment. In this case, we've got reconversion because we're recycling back some of the uranium, fuel fabrication, and then we've got a bit of storage, but then we reprocess, as we refer to it. That's our term we use for recycling, and we recover some of the plutonium and the uranium. And in fact, what happens there then is the waste that we deal with are different. So before we had a single waste stream, which is the actual fuel itself that needed to be disposed of, but now as we reprocess, the actual processing and chemical techniques that we use will split that into three categories. So we've still got waste, so the W refers to waste, and the L is level, and we've got low level waste, intermediate level waste, and high level waste. And it's this high level waste which is the stuff that contains all the real nasties, all those long-lived fission products, that's equivalent of spent fuel. Intermediate level waste does contain some fission products, but it's nowhere near as bad as high level waste. It could be dealt with in a certain way. And low level waste is very small amounts of radioactivity that can be cleaned up, and in fact in most cases chemically we can then release that to the environment. We're recovering the uranium and sending it all back to be made into new fuel, and the plutonium can also be made into new fuel as well, either for a thermal reactor, or perhaps ideally you will use that plutonium to perhaps kickstart your fast reactor program. So partially recycling also has its limitations, mainly because we're not actually recycling everything. We're probably only recycling about 30% of the equivalent energy output, because we're still leaving in quite a lot of those species such as the actinides, which can be used in a fast reactor, for example. We're saving quite a lot of uranium from being mined, and therefore, although most of the mass of uranium is in the tail stream, so we're still getting that anyway. It's only the enriched uranium that we're actually saving. And in terms of a ratio, from about 8 tons of spent fuel, we're probably saving 1 ton of new fuel. So we are saving quite a bit there in that regard. Ideally, like I said, we'd like to fully close the fuel cycle. Essentially what we would do then is there would be no need to do any enrichment. We would essentially breed all the fuel that we needed to do. And this is the only way you can do that is with fast reactors. So remember when I referred to as breeding, that in a normal reactor, in a thermal reactor, that was the act of creating plutonium from U-238. And you can arrange fast reactors to capture all those neutrons that leak out of the system, and you can use those to breed new plutonium to the extent that you can breed as much fuel as you're using up. I know that sounds a bit intuitively difficult to do, but actually it's quite possible to do that. What we do need though is full recycling of that material to be able to extract the fissile material and make new fuel out of it. And also ideally we need to be able to recycle all the transuranics, so it's all of the neptunium, the plutonium, americium and curium as well, in order to get all the absolute 100% of the energy back out. And therefore really all we're dealing with then is a fission product waste stream. The problem, of course, is the limitation here is the technology maturity, and in fact we've only ever implemented fast reactor prototypes. So we have built those in the 1970s and 80s in the UK, up at that site north of Scotland I mentioned called Dounreay. Similar situation in France and Russia and Japan and the US. So these were prototypes that prove you could do it, but not on a commercial scale or not as a sustained reactor, perhaps to generate power. And of course, one of the biggest things that we need a very high neutron flux to breed the Plut-239 from the uranium-238. And of course, when we've got very high neutron fluxes, we're also dealing with a lot of damage potentially to materials. So if we're completely closing the fuel cycle, here's a simplified version of that diagram I showed it right at the beginning. We're going to import our ore. We're going to create some fuel to begin with just to kickstart those reactors and get that plutonium. We're going to put it into a power station. There's our spent fuel, and then we're basically going to recycle around this loop. And those fission products will go off to waste management and disposal. And ultimately, of course, we will have waste that result from decommissioning and cleaning up our redundant facilities. So like I said, the limitations mainly on closed fuel cycles are the fact that we've got the lack of technological maturity, especially when it comes to the reactors. However, it's also the case with the recycle technologies. We're still working on what is the best actual recycle technology to achieve the separations we're looking for. At the moment, because fast reactors, the ones that have been built, aren't really proper commercial power reactors, they're uncompetitive equivalent in terms of the pound per megawatt hour with thermal reactors. And of course, if you've got very low prices for uranium, if it costs you very little for your fuel to fuel the reactor, then why would you pay for the cost of recycling? Unless, of course, you were driven from perhaps public perception or regulatory pressure because of the environmental benefits. However, in the long term, the only way we can have a sustainable nuclear fuel cycle for fission is using fast breeder reactors.